Performance of a distributed algorithm can be measured by two metrics: message complexity and time complexity. Message complexity counts the number of messages sent. But what about the time it takes? A distributed algorithm in general is running forever, which means that the number of messages is potentially unbounded. So how to proceed? The way forward is to focus only on one operation from start to completion. In the case of broadcast abstraction, this is from the broadcast event to the last process delivering the message. So message complexity, it is the number of messages required to terminate an operation of an abstraction. For example, in the lazy broadcast algorithm, the number of messages initiated by the broadcast until a deliver event is issued at each process. So these are the number of messages we want to measure. In most algorithms that we study, the size of a message is some constant number of bytes. But sometimes the message size can be a function of a quantity meaningful for the algorithm. For example, the number of processes in the system. We have, for example, the vector clock algorithm, where the vector clock has a size proportional to the number of processes in the system. In this case, it is more appropriate to talk about bit complexity. So what is bit complexity? It is the number of bits sent if messages can vary in size. So how to measure time when we are talking about time complexity? In sequential computing, time complexity is not expressed in physical time units, but as a number of some abstract instructions performed by the algorithm. For example, the number of comparison operators, lesser or equal, performed. In distributed computing, we have processes performing computation steps, like internal actions and output actions, and channel performing delivery steps of messages. However, in the asynchronous systems, transmission delays of a message until delivery are unknown. So how to proceed? First, we assume that the computation steps by a process is negligible compared to transmission time. This is true for most of the algorithms that we discuss in this course, but it is not true in general. Second, we measure the transmission time by a form of an abstract time unit. One time unit of an execution E is the longest message delay in that execution E. And we take time complexity of an algorithm to be the maximum time taken by any execution of the algorithm under the following assumptions. So what are the assumptions? A process can execute any finite number of actions or event in 0 time. So it is actually executing in some negligible time. That's why we approximate it to 0 time. And the time between a process doing a send on a channel and the delivery of that message is at most 1 time unit. So in most algorithms that we study, all communication steps, this is that we just mentioned now, will take 1 time unit. In some algorithms that we will not study in this course, if you assume some communication steps take less than 1 time unit, actually you can get a total execution which is longer, takes more time than the one that only assumes exactly 1 time unit. But this we will not discuss in the algorithms that we study in this course. We will not see this. So let us look then to this. So here is a way to see how long time it takes an algorithm. And we take a very simple one. It is the best ever broadcast. So the best ever broadcast will take 1 time unit from broadcasting a message by a process P until the last delivery of that message. And that is what we call also a communication step. But let us see it. So here is a situation where we have 4 processes. P1 does a broadcast, and this broadcast action takes 0 time units. Now this send action at this point, it is still local at the process, so it takes 0 time units, and the other sends. So we have associated a 0 here, a 0 here, and a 0 here. Now, this delivery on the other hand, so the delivery from process P1 to P4, this will take at most 1 time unit. So this is less than or equal 1 time unit. And this will still continue. So this is the time at this point is less or equal 1 time unit. Now the message arrives to P3, also will take less or equal 1 time unit, that is at most 1 time unit. And this event, the delivery pip up, is a 0 time unit, so we still have less or equal 1 time unit. The same thing here, this delivery now we get about approximately 1 time unit, so this is still the same here. And this is, we say, okay, it's at least 1 time unit. And this we say that it takes about 1 time unit, this is equal, and that is the case. So at most, this computation takes 1 time unit. And that's what we call the time it takes for a communication step. So we have 1 communication step, and that is 1 time unit. I just want to remind you with some other concept that if you see it, so you will not be surprised. It is the concept of using big O notation. So what is a big O notation? It is the upper bound of the asymptotic behavior of a function, Tn, when n grows large. So when we say that T of n is equal the order of G of n, we say that when eventually for a large n, T of n is bounded above by a constant times G of n. So let us draw that to understand. So here we have n, and here we have the functions. Here is, say, G of n, and here is our function T of n. And now if we multiply G of n by a constant, say the constant 2, we get this function. So this is 2 times G of n, and we say that this 2 is C. The cross point here is n naught. So what we are saying now is T of n for large n, n greater than actually T naught, is bounded above by a constant times G of n. And that's what that is, G of n. It's a constant times G of n. So T of n is equal O of G of n if there exist constants. This is in the case C and n naught greater than 0. And for all n greater than n naught, I mean up to this point, is here. So C times G of n is greater or equal T of n. Okay, so that is the meaning of a big O notation. So the big O notation says it is a function that is always an upper bound of what we want to measure. So for example, given n processes and an algorithm A, we can say that the number of messages is of the order of n squared. It means there is some constant times n squared when n is large that is always bigger than the number of messages that this algorithm sends. So it means A of n sends at most some constant times n squared messages.